Okay, now I think we're finally. Oh, not quite set up. Sorry. Made this computer angry. All right, now I think we're ready. So last lecture, and then as I mentioned, so we'll still do a review on Monday if people are interested and around. Sorry, I have to fix my mapping again. So review Monday officially. And then I don't know if people want like office hours on Wednesday morning, like during lab time. Like I just kind of put a question mark. I mean, I'm available, so maybe that could be an option. I feel like a lot of people in this class are trying to get the exam done this week, but I mean, it's totally up to you. Otherwise, that could just be a good session to catch up. And then the in-person exam will take place a week from today. But like I said, I've been seeing the count go up on my Blackboard just today even. So I think some people are already doing that. So yeah, if you want to do the online one, that's fine. If you want to take both and take the highest score, that's fine. I'm here for all permutations, combinations. And I apologize, somebody did ask, I mean, there's been a few requests to try to fix the quiz thing. I know the quiz is out of 15 instead of out of 10, but Blackboard is not letting me change that. So I apologize, but yeah, I really don't know what to do about that. But that's why I'm trying to move away from Blackboard. But try not to stress about your grades. Like I said, just turn everything in and the grade should come out okay. Other questions, comments? Yeah. Okay. Well, we could talk after class. I mean, we did skip some assignments and yeah, I mean, Blackboard, like I said, is kind of a disaster. But well, it's just Blackboard. That's why. That's like literally why I'm like trying to reprogram it for my open math because Blackboard. Oh, they're still missing. Okay. Okay. I thought I had like reconciled, but I can reconcile again. Like I said, they don't talk, which is the other problem. But yeah, just give me like this weekend to try to fix stuff, and then you can bug me on next Monday about what's still incorrect. All right, let's finish up the chapter on that note. And then, like I said, after class, like today would be good to try to like figure out what I am missing. I've been trying to update grades. I think I caught up on most of the in-person stuff, at least like physically that was handed to me. And then I think there's a bunch of Blackboard stuff that's coming next. But yeah, let's sort that out after lecture today. All right, so looking at our last chapter here. So let's go back. And so we've been looking at acids and bases. And so now there's this thing called a buffer solution, which you did look at it in lab pretty briefly. It was like the acid-base lab. And so a buffer is defined as a solution that resists changes in pH when our acid or base is added to the solution. And so we'll kind of see how this works out. But a buffer kind of works by it first neutralizes our acid or base that's added to our buffer. And then we kind of have Le Chatelier's principle that brings it back to kind of equilibrium. And so the key components of a buffer is that we have to have our weak acid and our conjugate base. So for example, we could take acetic acid, like vinegar, and then the conjugate base would be sodium acetate. So that'd be one example. Or we could do the weak base and the conjugate acid. So the weak base would be like ammonia, for instance, and then the conjugate acid would be ammonium chloride or some sort of other salt there. And so your blood, for example, has some carbonic acid, and then we have our hydrogen carbonate ion, and that is our buffer system. Again, there's just a difference of a proton there, right, between our acid and our base there. And so now this is just kind of going over again how we would make our acidic buffer solution. And so like we mentioned, right, it has to have our weak acid and conjugate base. And so that's what was selected, our acetic acid and sodium acetate, and then they're added in a certain ratio and molar amount. All right, so some of this stuff is wordy, but it's just trying to show us kind of what's going on. So let's look at this. So it's saying, okay, let's say we take our acid here. So again, this is vinegar or acetic acid. And then we react it with sodium hydroxide, right? So it's saying, okay, we have our buffer. A base is added. That base is going to react with our acid. But everything's in equilibrium, right? We can kind of, I'm trying to rewrite it as well, just so we can see the chemistry a little better. So plus sodium hydroxide. So this hydroxide deprotonates this, leaving us with water. And the sodium acetate. So that's what's shown here. But remember, this is part of your buffer component as well. And so kind of looking at this, right, so okay, if we add our base, well, we made our conjugate base, and so then our equilibrium, right, could shift a little bit, so maybe it will then kind of reform some of the acid after, right? So we mentioned we're kind of thinking of this reaction in both ways, right? So, okay, even though we did make this deprotonated species, right, when we added the sodium hydroxide, this acetate can go on to reform acetic acid, so that helps, again, kind of buffer out your pH and your solution. So there's Le Chatelier's principle. And then, okay, similar effect if we add a acid, except the acid component in this case will react with our conjugate base. So let's just kind of sketch that out. So now strong acid, and now it's going to react with our conjugate base formally, and I'll just abbreviate as H plus. We have, right, our sodium acetate, and then of course, right, this hydronium, and so that will just get reprotonated there to reform, right, our acid formally, and then plus the salt, right, of sodium chloride. And then again, Le Chatelier's principle, so we can kind of buffer out the effects. Again, we know that in solution, right, this can disassociate to reform hydronium and the acetate once again. So everything's, right, just equilibrium. So that's what you're thinking of. It's kind of going back, forth. It reacts, yes, but then we have Le Chatelier's principle, equilibrium. And so that's how we, again, keep our pH relatively unchanged, or in the case of our strong acid, and our conjugate base, our pH, will decrease slightly or not at all. And then, okay, well, this also makes sense so that we can overwhelm our buffer, right, at some point. So we're saying that the HCl that we're adding is less than the amount of our base, right? So of course, at some point you could overwhelm your buffer in either direction, and then you pretty much just destroy it at that point. And so that's going to depend, right, on like the molar amount still. So how many moles are in there? So that kind of gives us, right, our buffering capacity, we would say. All right, so that's kind of Le Chatelet's principle. And then if it does come up on the exam, the most you would have to do is this Henderson-Hasselbalch equation. I don't remember off the top of my head, though, how heavily it's covered on the exam. I would have to look. And let's see, we didn't do an example of it. Oh, geez. I was just trying to pull up your exam really quickly. That didn't work. Okay, buffer. Okay. So generally how it works then, let's do a quick example. And so we could go do something like we want to make a buffer. So what is the pH of a buffer solution that contains 0.1 molar sodium acetate and 0.05 molar acetic acid. And the pKa of acetic acid, let me look that up. I want to say it's like 4.76, but I want to make sure. Yeah, or on an exam I would provide it. So yeah, it was 4.76. And then, well, we might have to walk through it together. But this would be how the question is asked. And then this is the equation. And so all we have to do is identify who's our base, who's our acid, and then plug it into this expression where we're given the pKa, and then we just take the log. And so then we want to plug in molarity values. Yeah. And then, right, kind of remember, okay, well, sodium acetate's my base. This is my acid. Obviously, on an exam, right, that would kind of be the, I would say, hardest part is like, okay, well, who's my base? Who's my acid? So plug that in for a second. Yeah, so this is the base, this is the acid, and then you just plug those two numbers in.
So when it says base and acid in the equation, that's talking about the number of moles?
The molarity. Yeah, so you plug in the molarity, so the concentration is what that bracket means. So really all we have to do is pH equals 4.76 plus the log of our base, which we said was sodium acetate, so 0.1 molar over 0.05 molar. And that is the hardest that it will get, if we even cover it. Like I said, I don't remember There's probably one problem on your exam, if I remember correctly. And then I get like about five for the pH. And looks like that's what other people got. Just again, test your calculator, make sure you know how to work it. You don't want to have something weird going on. So just make sure you're plugging it in. All right, we'll try to do this one relatively quickly, but and so again, there might be like one or two questions on this. And this has to deal with like, okay, what's a strong acid? What's a strong base? And so going back to some of the things we had talked about on Monday, I'm trying to find it. Right, so we had said, for instance, that HCl is a strong acid, so right, it fully disassociates, which means that our chloride can never reform HCl, so that makes it neutral, versus all these other salts. And so maybe I had done a poor job of labeling. I think I have, at least I thought I had some extras. Oh, well, now I don't know where they went. I always have too many papers floating. If you didn't get one of these cheat sheets, get one probably later. But now we're going to see that all these ions here, not hydroxide, but carbonate, cyanide, so not water, sulfate's kind of strange, but most of these, right, are then going to be our weak base salts. And so we'll come back to this page. Okay, so now let's go back to these notes and what it says. And let's kind of go through what it's saying, but then we'll see like how we can identify it more rapidly. And it says, okay, if our salt cation is the counter ion of a strong base, and so that means, right, it came from a base that fully disassociated. And I like to do this analysis, at least when you're starting off. As you go through it, you'll kind of know the answers. Okay, so sodium, right, it comes from sodium hydroxide is a base. So it's basically, right, the conjugate acid of this base, except this base, right, fully disassociates. It's strong. Equilibrium lies all the way to the right. So this sodium is never going to reform anything, right? It's never going to pluck off the hydroxide and leave like H plus ions in solution. So this is considered neutral. Those birds making a new nest there. Yeah, I forgot what species of birds they are. They like to make nests there. And then 1 year, facilities took down the nest. I think they're technically protected. Anyways, bird season. Okay, so then the other half of that, the anion, is a conjugate base of a strong acid. Okay, so let's look at that, right? So that's saying our chlorine is from HCl. Again, strong acid fully disassociates. So like we established earlier, this chlorine is never going to reform HCl, right, and leave hydroxide. So this is neutral as well, making sodium chloride an overall neutral salt. So does that make sense for our first analysis? Why it's neutral? Like I said, if it is, it'll be like maybe one or two questions. Uh, I would have to pull up like both versions of the test and look. So let's try another one. So let's look at calcium nitrate and we'll do the same analysis. So now calcium nitrate. So let's start with calcium. So what base is calcium paired with? And well, just like if it was with a base. So basically like hydroxide. And then is that a strong base or a weak base? Well, I guess we're asking, does it fully disassociate? It should though, right? It's like a fully soluble, it's an ionic compound. So this fully disassociates. And so that means, right, that the calcium's not going to reform calcium hydroxide or the base. So that makes calcium neutral since it comes from a strong base. So same thing. So what acid does nitrate come from? Yeah. And then so nitric acid, do you remember if it's a strong or weak acid? So strong, so good, so right, fully disassociated. So same thing, this nitrate is never going to reform our nitric acid from water. And so that makes nitrate neutral as well. And then we can conclude calcium nitrate is neutral. And like you could also start making a cheat sheet if this is kind of confusing, right? So then you can start saying, well, my neutral cations are going to be, right, lithium, sodium, potassium, magnesium, calcium, strontium, rubidium, right, etc. So like your alkali metals, group 1 and 2, that's kind of what we're getting at, is like most cations are actually neutral. And maybe I should add that. So most cations are actually neutral salts. So that's what we're getting at with this whole conclusion. Uh, oh yeah, etc. But right, it's most of our metal cations. And then the anions, right, like we said, the anions are either basic or they're neutral. So right now we're only looking at neutral salts. And right again, go back to the cheat sheet, and these are our neutral salts, right? Nitrate, chloride, bromide, iodide. So that kind of helps you there.
And how would we label it if, like, the cation is weak, but the anion is strong, is neutral?
So like this case, ammonium chloride.
Uh-huh.
Yeah, so then once we get to it, so let's skip to ammonium chloride. So like you brought up, right, ammonium is from ammonia. So let's scroll down. So now we're looking at ammonium chloride. And so to your point, right, this is one of our few acidic cations. We can tell why because, okay, what base did it come from? Well, it came from ammonia. And ammonia, though, does have, right, that equilibrium. So sorry, first I'm just making ammonia to show where it came from. But then what we want to show is that ammonium in the presence of water will then be deprotonated to reform the ammonia and then the hydroxide. Or, sorry, not hydroxide. Hydronium. Sorry, I said that wrong. Hydronium. And so this is what defines it as an acid, right? Because we made H plus in solution. So that's why this ammonium is acidic. And so for our purposes, like that's the only acidic salt we will see. is ammonium, or like I said, you won't be tested over it, but it's down here on the example. I'll kind of reveal this. Hint, hint. So this is basically an ammonium derivative, and if I were to write it out, so that's what this looks like. And so this is methylamine, by the way. And if you watch Breaking Bad, did anybody watch Breaking Bad? Yeah, well, if you watch do you remember the methylamine train car episode? Well, the basically everything goes back to meth, but they at one point steal methylamine as a precursor. It's just a methylating agent to make meth. But yeah, it's a whole train car scene thing. So that would just be the acid salt of methylammonia. But really, if there's one takeaway, meth is easy to make. No, don't do meth, kids. All right, so then, sorry, finishing up your question. All right, so we established that any of these ammonium salts are acidic. We see why. Ammonium, sorry, yeah, correct. So the salt is acidic, and then ammonia is the base that it came from. And then chloride, once again, right, we saw that earlier. That's from HCl, the strong acid. And so our chloride is neutral. So then overall, the salt is acidic. Does that make sense for that example? And and then we won't see, so it's in the example here, and it brings up, well, what if you had, so right, ammonium is acidic. Fluoride will look is a basic salt, but we'll look at why in a second. And we're not going to do this. Basically, you have to compare, right, their Ka strength versus their base strength. That's just like a little bit too much for us. I make the 200 level do it, but it's okay. Just know that you would have to compare like who's stronger, but we won't be looking at those cases. All right, let's try to look at our other examples. So trying to do it a little faster. So KBr, for instance, let's just run through that. So potassium hydroxide, strong base like we established. So potassium is neutral. Bromide is from hydrobromic acid. Again, another strong acid. We could go back to this cheat sheet chart. Oh, there's bromide, right? Do not undergo base ionization in water. So that's also a helpful hint. So that's neutral. So overall, neutral. All right, looking at our next case. And so our next case, we're still going to have our neutral salt cation, right? So it's saying the salt cation is a counter ion of a strong base. Okay, so that's what we've seen, right? All these neutral cations like sodium, calcium, and potassium. But now it's saying, well, let's look at our anion. And the anion has to be the conjugate base of a weak acid. But notice these anions. So we have fluoride, acetate, and nitrite. So if we go to our cheat sheet, well, there they are. And so fluoride, nitrite, acetate. And so since they're in the middle here, right, they do, again, undergo this ionization to reform their acid. And again, that's why these are our base salts. So I hope that cheat sheet helps. So let's look at sodium fluoride again. I know we've looked at fluoride, but it doesn't hurt to look at this stuff again. So sodium, again, sodium hydroxide. strong base, fully disassociated, so sodium is neutral. But then fluoride comes from HF, which is weak, right? And so all this is saying is that our fluoride will reform HF. Just another reminder of the safety dangers of fluoride salts. So now we reform HF, we make hydroxide formally, and then definition of a base is that formation of hydroxide. So our fluoride salt is basic, leaving us with sodium fluoride as a basic salt overall. Does that make sense? And then let's do the same for acetate, just to see it again. So calcium acetate. And I don't know why I can't remember like the formula for acetic acid, but I can just draw it out. So there's calcium acetate. So calcium acetate. So our calcium, still from calcium hydroxide, fully disassociated. So calcium is neutral. But the acetate, like you remember hopefully from the buffer, so the acetate comes from acetic acid, so then it can reform our acetic acid, making a base though as well. And so that leaves our acetate as a basic salt. And then calcium acetate is overall basic. Does that make sense? And then same thing. So calcium nitrite, again, we could write out that process, or again, go to our cheat sheet. Okay, we have nitrite, so we know that it'll make nitrous acid. So again, this is a base. And so then, right, NO2, it's basic. All right, good. And then the last little bit, okay, we looked at our acidic solutions, and then other acidic solutions can also come from what's called these highly charged metal species. We're not going to be tested over them in this class, just kind of building awareness. And so the classic example is aluminum, and aluminum is considered highly charged since it goes into the 3+ oxidation state. That being said, this is not, again, a full picture of aluminum. And technically, aluminum is amphoteric, but we won't go into all that in this class. So, yeah, aluminum can like bind water and hydroxide. So let's see if we can do this example real quick. So see if you can do, well, really we would be testing on A. I said I would skip the metals probably, but you can still guess that one. And then C, I kind of gave you the hint at already. D, and then we're not going to do E, right? Because E was comparing who's stronger. So at least try A, B, C, D. Then we'll go over the answers real quick. So what do we guess for strontium chloride? Acidic, basic, neutral?
Neutral.
Yeah, so it should be neutral. So right, strontium's just from strontium hydroxide, so that's strong. Chloride HCl again, so again neutral for our chloride. So overall neutral. What about B? So we said that I probably won't test you over that, but what did we just learn about aluminum that we should consider it to be? Uh, or so then it would be. I didn't hear what you said.
Amphoteric.
Uh, well, they said acidic here, but yeah, you're right. Like amphoteric is technically probably the better answer, which is why it's like we won't even get into it in this class. But they want you to assume it makes an acidic solution. But like I said, probably won't be tested over that. What was this one again?
Ammonia. Oh wait, no.
Yeah, so it's a well, it's a kind of an ammonia derivative, so then that makes it
Acidic.
acidic. Good. So it's from our weak base, or again, a weak base derivative. And then this last one, this could have been tricky if you didn't recognize what this was, but it's just a formate. I don't know if that helps drawing it out. Hydrogen there. So then what's this guy look like? Remember this group?
So would it be an acid then?
So it's yeah, so it's from an acid, but then if it's an anion, it's a base. So yeah, it should be basic. I don't think we had this on there, but yeah, so right, this is again our formate. So this is the base of formic acid, and since it has this little negative charge, right, since it's balanced by this sodium, then we know it can react with water to reform formic acid. And just again watching out for that carboxylic acid group. Or this when it's deprotonated, it's the carboxylate. So going back and forth between the carboxylic acid form and carboxylate. Questions on those? All right, let's finish up with titration. And so the last bit, I mean, you did a titration, so that was really good. And so there's all sorts of titrations. Again, y'all did a pretty simple one, just an acid and a base. And so kind of, before you even got to the titration, kind of the question is, well, what are you trying to titrate? What's the reaction? What's the end point? How are you going to know you're at the end point? And that can obviously vary depending on what your substance is. And so you have usually some unknown solution. This could be used to titrate like other molarity of like reagents, for example. Sometimes like chemists have to titrate certain things. I'm just like N-butyllithium. There we go. N-butyllithium, for example. Um, this is something. This would be a real-world example of an unknown solution. So N-butyllithium is a pyrophoric chemical, and you can purchase it in different molar amounts. commercially, so anywhere from like 1.5 molar to like a 2.6 molar solution. But the whole point is like it degrades. So then sometimes, depending on your reaction, a poor, unfortunate chemist may have to titrate it and really dial it in and make sure that it hasn't degraded too much. So that's one example of like other types of titrations other than like your acid base titration. And so that goes into, right, like what an appropriate indicator was. So that's why we use the phenolphthalein, since the phenolphthalein has that indicator point around 7 or just after 7. So that tells you when, in your case, the acid base moles were relatively equal. And so here is again your titration setup. In this case, we're titrating our sodium hydroxide into our acid solution, and you try to get it as kind of pale pink as possible to be right at that equilibrium. Even that I think is a little too dark. And then we just want to appreciate some of these curves. So if you have a strong acid and a strong base titration, that just means your pH will start off really low, and then boom, it'll shoot up, right? And I think a lot of you saw this if you were in lab and doing it, right? You're just kind of like dropping, dropping, dropping. Nothing's happening. Then boom, like the whole thing's super pink. And that's because, right, once you hit that equilibrium, you're just shooting up. And then, right, that causes your pH to rise pretty dramatically as you shoot past that equivalence point, and then you're going to be super basic there. And then the only other things to kind of appreciate is the gentler curves of, let's say you did a weak base and a strong acid. It just starts off kind of less basic, equivalence point around, and then it's not at 7, right, for their equivalence point. And then again, right, not going as low with our pH. Same thing with weak acid, strong base, right? You're going to have an initial pH of closer to 4, and then equilibrium point, and then back to excess hydroxide. And then if you had a polyprotic acid, then you would have kind of 2 inflection equivalence points. But like I said, we don't really need to go into too depth. Maybe take my 200 level class. Even then, we don't go too much deeper. This can get into like more advanced equilibrium and then like analytical chem stuff. And then again, okay, all these indicators, we're just appreciating that some of them, like thymol blue, have 2 transition points. So one at the lower end and then at the higher end. It just depends on the compound itself, right? And how sensitive it is. And then again, right, so many different indicators. And then wherever you're looking to dial in your pH, you can pick the appropriate indicator. All right, I promised some stoichiometry practice, so let's at least try to do 1 or 2. So let's try this one. And this would be a good example of a question asked on an exam. Should be somewhat similar to our lab concept. Let me make that bigger. So what volume of 0.15 molar sodium hydroxide solution is required to react completely with 50 milliliters of a 0.2 molar HCl solution? So set up your balanced equation. Kind of how would you set it up? Think back to our solution chapter. So let's go through this together. And the first thing you want to do is just write out your balanced reaction. This one, at least, is relatively simple in that they're in a 1-to-1 ratio, right? And so let's just kind of think of, well, what if this had been like a diprotic acid, like sulfuric acid, right? I just want to point out that the equivalence for that would have been 2 equivalents of sodium hydroxide. But right here we're looking at a 1-to-1, so just kind of keep this in mind if you were to see a diprotic acid. So just trying to keep you aware of all the tricks. Okay, but we're just looking at a 1-to-1 ratio. Good. And so then we want to see how much sodium hydroxide we need. And there are a few other tricks and ways to get there, but I'll just kind of do it the formal solution. And so let's first find moles of HCl, right? We know that one. And then that sounds good. And so I'll have to plug it in. And right, so molarity is moles over liters. So then you just multiply that by 0.05 liters. And then, so that should give you what you said. Like I said, that sounds correct. So you said 0.01, so good. So 0.01 moles of HCl. And then, okay, back to our balanced equation, 1-to-1 ratio. So we know we need 0.01 moles of NaOH. And then depending how you want to set that up, you know, you could set up a proportion. So you have 0.150 moles in 1 liter. So if I need 0.01 moles, we could solve for X. And then, so then we should get that many liters. So multiply it by 1,000 to put it back in milliliters. So about 66 milliliters for our answer there. Questions about that one? All right, I almost forgot about our demo. So let's do our quick demo. That's weird. Oh, okay. I must have hit my camera. That's okay. All right. Trying to pop out. There we go. Hopefully this camera's working. Yes, it's alive. Can never tell. All right, let's look at our demo here. So I promised that I would bring okay. OBS said it reconnected for a second. I admittedly did not plug in. All right, safety tip 2, right? Don't. So you'll complete the circuit with your hand if you do, which I have done before, which is not fun. And then you never want to complete it across your body. Sorry, I'm trying to clean this out just a little bit. All right, so let's start down the line. And so I have, well, maybe I should pour these out so we can move fast. Oh, they parafilm this way too well. Oh, I'll pour them as we go. All right, so we'll start with water. So pure water, right? Nothing happens. That's what we expect. No ions in solution. Okay. Next one is sugar. And so that's a non-electrolyte solution. So same thing. No ions. So now let me rinse it. So the next one that we have, so I poured out acetic acid, and I made sure to bring, I couldn't find exactly the same molarity, but I brought 4 molar acetic acid, I brought 3 molar HCl, and 4 molar sodium hydroxide, so you can compare. And so let's start with the acetic acid. And do you see how weak that is? It's like barely going, even though, so you can see it in the video. But it's like kind of crazy to think about. It's like that's a weak acid, right? And so you can tell it's not, it's barely disassociated. Uh, Again, take my 200 level class if you want to quantify it. But it's really showing you that there's not a lot of ions disassociated. Then I'm just trying to clean it in my pure water before I mix everything. All right, so then next down the line, put that back. So here is the HCl. So lower molarity, right? I only found the 3 molar ready to go in lab. And let's look at it. Whoa! I'll put it on camera. So that is, right, super bright. Again, fully disassociated. You can really appreciate that. And look, it even contaminated my pure water now. I'm trying to clean it. No, so much for my pure water now. Okay, trying to clean this before I do a mini reaction. And then the last two, so here's some sodium hydroxide. Let me put it on camera. Sodium hydroxide. Sugar. So again, same thing, right? Super, super bright. And it messes up my water. Just trying to clean it. And then last one for good measure. Again, we saw this one in lab. This is only a 20% sodium chloride solution. Let me clean it some more. So now back to the salt. And so right, salt, again, sodium chloride, fully disassociated. So light, nice, and bright there. All right, that's all the entertainment I have. But that's at least a good full spread of that. So usually online, like they don't do all of those solutions if you look at like other videos. All right, I think that concludes our last official lecture. So thank you all again, and thank everyone for their hard work. Again, I know everybody is everywhere, online, in person. I appreciate it. I appreciate all the open math feedback. And then I do have one last quiz if you're in person. Otherwise, you can take it online. So I'll hand out the quiz, and then otherwise you're free to go. And then, okay, so you're taking online. Are you going to take it? Okay, online. Are you taking the quiz online? Okay. Sounds good. But yeah, if you want to hang around, I probably have papers too to give back. I did have one no name as well. But yeah, just check your grades and get those in. So thanks again.